Welcome to the AP Physics. This is on Unit 4, Energy. The topic is going to be energy in an open and closed system. Energy. Energy is defined as the ability to do work. But we already know what the definition of work is, so we can substitute the definition of work in. We could say energy is the ability to move an object with a force over a distance. The unit is 1 joule is equal to a Newton times meter. Newton comes from the force, meter comes from the distance. That's why a joule is considered a Newton meter. There are two types of energy that we're going to work with in AP Physics 1. The first one is your mechanical energy, and that is the energy associated with physical movement and the position of an object. If an object is moving, that is moving mass with a speed. So this has a mass, so an m, and a speed, which is a v. That's why the equation is k equals to 1/2 mv squared. K just stands for kinetic energy. Next are your two potential energies. The first one is the gravitational potential. This is defined as the energy that is stored by displacing the object away from equilibrium. Here, the displacement is in the vertical direction, so it is mgh. M stands for the mass, g stands for gravity, and h is the displacement away from equilibrium in the height direction, in the y direction. So sometimes you might see this as ug equals to mg delta y. That is also it, because height is basically the change in the y direction. Now we could talk about a displacement in the x direction. This can be seen in a spring potential energy. The spring potential energy is the energy stored by displacing the spring away from its equilibrium. In this case, it would be delta x. The spring potential energy is 1/2 k delta x squared. The delta x is the displacement in the away from equilibrium. There are other types of energy. These are your non-mechanical energy. Things like thermal, which is the hotness that comes from rubbing of a surface, and friction. Drag, which is the type of friction force rubbing and colliding with the air molecules in the air. Sound, which is the compressed sound waves. Also your electrical, chemical, nuclear, and radio. Electrical energy is basically what is powering your light bulb. Chemical can be like burning of gasoline or burning of propane. Nuclear, you could see as the breaking of nuclear material. Radiation is like the sun shining down. The laws of thermodynamics. The law of thermodynamics, the first law, talks about the conservation of energy. This states that energy can neither be created nor destroyed, but merely transferred from one form to another. We have two types of systems. We have either the closed and the open. The first one is the closed. This is when the energy in the system is only transferred and transformed within the system. Like this. Notice that the transfer is occurring between the mechanical energy, and the three types are kinetic, gravitational, and spring potential. Notice that the total energy here remains constant. So if the system has 10 joules, no matter in what form, it's always going to stay 10 joules. The open system can be seen as the energy in the system is transferred and transformed in and out of the system. Like this. There are energies coming in, the blue line, and out. The transfer between mechanical energy and non-mechanical energy, so things like thermal, drag, sound. And in the process of it being open, the total energy does not remain constant. Now we're going to take a look at a specific scenario for the closed system. Here you have the definition again for the closed system. The energy in the system is only transferred and transformed within the system. This scenario is when a ball is being compressed by a spring, then released, then it goes up a ramp. There's going to be a transfer between the mechanical energy, and in this entire process, because it is a closed system, the energy remains constant. As the start, a ball is being compressed, so the energy stored by a displacement from equilibrium is in the spring. So for example, I'm going to say this has 10 joules of energy. Okay, this is just an example. Then once I let go and release it, it's going to start moving due to Hooke's law. And then the ball's going to get released, and now all the potential energy is going to move to kinetic energy. It's going to go with 10 joules of energy, because here all the spring is now transferred to the kinetic energy. This is considered kinetic energy because you have a mass and it is moving. 1/2 mv squared. Once it hits the bottom right here, it's going to be at its maximum height, and it's going to go up the ramp. As it goes up the ramp, it's going to start gaining gravitational potential. Why? Because there's a displacement of height in the vertical direction. So now, as it goes up, it's going to gain gravitational potential. As it reaches its highest point, you could say that here it has all its gravitational potential at 10 joules. So notice that the total joules of energy, the total energy remains constant at 10 joules, no matter what scenario it is. When it's either at the spring, it's still 10 joules. When it's kinetic, it's still 10 joules. And when it's gravitational potential, it's still 10 joules. No energy was lost, merely transferred from one to the other. Now we're going to take a look at an open system. Notice an open system, there's going to be a transfer between the mechanical energy and the non-mechanical energy. The total energy does not remain constant. So it is like a block that slides. So right now, the block is going to move. Okay, as it moves, there's going to be a kinetic energy. So let's say this now is at 10 joules. As it slides over friction, it's going to start heating up. So energy is going to be starting to be transferred. So now here, when it is over the surface, it has both kinetic and thermal. So in this case, let's say it would be 8 joules of kinetic energy, and there's 2 joules of thermal energy. So in the end, as it gets out of the friction blocks and goes to the non-friction block, the total here is 8 joules. Notice, originally, it had 10 joules of energy within the system. Afterwards, we had 2 joules of energy leave it in terms of thermal. So notice that the total energy does not remain constant. It went from 10 to 8 because there was a loss of 2 joules due to friction. On the AP Physics test, you will see this as they will say the system is open because there is a net force exerting on the block. That net force is due to friction. Let's see, from this example, we saw that the kinetic energy changed. It was at 10 joules to 8 joules. We're going to see how that works. Here's the scenario. A 1,200 kilogram car is moving to the right at 20 meters per second at the start. After 100 meters, the car's new speed is 34 meters per second going to the right. 1. What is the distance traveled? 2. What is the work done by the car? Hint, you're going to use the work formula using the force. 3. What was the car's initial kinetic energy and final kinetic energy? And lastly, what is the change in the kinetic energy? Well, number 1, you already know the distance is 100 meters. But number 2 asks you to use work. So you're going to have work equals to force times distance. Do you have a force? Well, you have a mass. you need the acceleration and distance. So you need the acceleration here. So we probably want to use our kinematics equation to get our acceleration. So this is the kinematics equation you would use, solving for A by dividing 2 delta x over to the other side. Plug in the values and you get A equals to 3.78 meters per second squared. This is the acceleration of the object. Why do you need the acceleration? Well, because you're going to plug it in. Work equals to force times distance. Work is equal to mass times acceleration times distance, because that is what F is. Plug in the values and you get the numerical value of 4.5 times 10 to the 5th joules. This is the amount of work done by this car. So what is the car's initial kinetic energy and the car's final kinetic energy? Well, we know the equation as 1/2 mv squared. We plug in the values. The mass is 1,200. The initial velocity is 20. You get 2.4 times 10 to the 5th joules. What about the final? Same equation, 1/2 mv squared. Plug in the values. The new velocity was 34. And you get the k is equal to 6.9 times 10 to the 5th. We know that the change is defined as final minus initial, so k minus k naught. Plug in the values. You should see that delta k in this case is 4.5 times 10 to the 5th joules. There should be something that you notice. Notice number 2, the work done in this scenario is the same as the change in kinetic energy. This leads us up to our core concept that the work energy principle states that the net work done on an object is equal to the change in the object's kinetic energy. So the work done can be seen as force times distance, or it can be seen as work is equal to the change of energy. Because once you apply the force over a distance, you're technically releasing kinetic energy. This is what it looks like, and we use the net for the work. Now, let's take a look at question 5. Is the system open or closed? Well, we saw that the initial kinetic energy was 2.5 times 10 to the 5th, and then we saw the final kinetic energy as 6.9 times 10 to the 5th. There was some form of change. The kinetic energy of the car actually increases over time, but where does the energy come from? Well, in this case, the system is actually open. How is it open? Well, our initial was 2.4 times 10 to the 5th, but our final was 6.9 times 10 to the 5th. What happened? There was an increase in the energy. Where is it coming from? The burning of gasoline. The system gained energy by burning of the gasoline. The system was open. Energy came into the system. That's the only reason why kinetic energy could increase. So we would say that here, the work, which is the difference between these two values, was 4.5 times 10 to the 5th joules. That value is positive. That means energy is coming into the system. Energy coming into the system will speed up the system, will introduce more energy into the system. So we saw that the in blue shows a scenario where work is positive, energy is coming into the system. As a result, the object will move faster. What about if we look at the opposite side of things? The car now applies a brake and slows down to 6.8 meters per second. What is the new kinetic energy? Well, if you do the math, you get 1.7 times 10 to the 5th. That is the new kinetic energy. Well, we saw that it's actually lower now. Originally, it was 2.4 times 10 to the 5th. Now it is less at 1.7 times 10 to the 5th. What happened? We would say it actually lost energy, right? Due to friction. This is when the car applies the brake. So what is the work done? Well, we know work is the change in the kinetic energy. So 1.7 subtract 2.4 gets you negative 0.7. What is the negative in work telling you? it tells you that the work here is negative. Energy is actually coming out of the system. The object will actually move slower as a result. Now, let's take a look at this graph. Here we have a scenario. You're going to graph the total energy at every given step in this scenario. Remember, the floor is rough and there's technically air. All right? So, the first part, you would see that here it's just a spring. Notice the spring is at rest, at equilibrium. So, there is no energy at all. The next scenario, a mass is attached and now compressed. A mass is attached and then compressed. This is where the UK is, which is the spring potential energy. We would say that the system is actually gaining energy from me doing work onto the system by compressing the spring. This spring isn't naturally going to get compressed by itself. Someone actually has to put work into the system. Someone has to put energy into the system by doing work. That's me pushing the block and compressing it. The second scenario. Now the block is released. All the potential energy that it had, which was UK, is now transferred to the K, which is the mass is released from the spring and now has kinetic energy. The energy transfers all the spring potential into the kinetic energy. Notice that the spring length returns back to equilibrium right here at x equals to 0. As a result, all the energy that the spring had when it was compressed, now released, is in the block, which is the kinetic energy. The block is now moving. Well, the block now all of a sudden slows down to a rest. Why does the block slow down to a rest? Well, the reason why the mass slows down to a complete stop is because all the kinetic energy is now gone. Where is it going? Well, it went to both thermal and drag. The thermal comes from the friction that the block experienced because the floor is rough. There's also air there. So there's air resistance. So the block loses some energy due to drag. We can say that the energy now transfers out of the system in forms of thermal due to friction and drag due to the air resistance. In this case, if we just look at the two middle steps where the mass is compressed and then released, we would say that in this scenario, the mechanical energy of the system of the block does not change. It goes from spring potential to kinetic energy. And in this case, we can say that the mechanical energy of the system consisting of the block and earth is more than 0 for it to start moving, but less than 1/2 kx squared, which is the spring's potential. 1/2 kx squared. Okay? It has to be greater than 0, but less than that value. So this is the mechanical energy of the system. But if we take a look at this shows the outside system as well. If we want to just look at the mechanical part, we only look at the kinetic energy, the spring potential, and the gravitational potential. Now let's take a look at the total mechanical energy of a system when it's in circular motion. The example you should see from before is a softball pitcher. The softball pitcher is swinging a softball at the end of her arm with a length r in a vertical direction shown. The ball moves with the minimum speed necessary to complete a circular path. Consider the system to just be the softball here. What you want to do is describe the mechanical energy of the system. Is it open and closed, and why? So if we take a look, we would say that the system is actually open because there's the net force exerting on the block. Where's that coming from? Well, if you have seen this, at the top of the circular path, there has to be a minimum speed necessary to overcome that circular path. There are two forces going towards the center. Force gravity and force tension. That is makes up the centripetal acceleration. So you could say that the centripetal acceleration, so summation of Fc, is made up of tension and force of gravity. Make the substitution. Force centripetal is MAC, and solve for A. Notice that this is the net force exerting on the block. If the system was closed, so this is when it is open, but in blue, this is what happens if it was closed. If it was closed, tension and force of gravity would cancel each other out. There would be no centripetal acceleration. So here you would say there is a net external force exerting on it, which is the centripetal force. The force of the tension and the force due to gravity changes the mechanical energy of the ball system. Also, the girl's arm is also exerting an external force on the ball as it travels. This shows that circular motion breaks mechanical energy of the system. It breaks in the sense that the system is open because there's always an net force exerting on the block, or in this case, the ball. All right, there you go. That is everything that you need to know about the open and closed system.